We now move to circular motions in orbit. Most of the circular motion has been done in the preliminary course, so it's a very quick retreatment. This will be referring to page 31 and following on your blue book. Okay, so let's start. This is the story so far. This is what we already know from the preliminary course. That an object moves in a circle because there is a force that pulls it in towards the centre. So here is the object in motion, and the object in motion, we are going to use a little m to represent that. Okay? If there is an object in the centre, which we call the central object of orbit, we will give that the capital M. So please realise that in this formula here, we are using a little m to indicate that the object, the smaller object, is in motion around a larger object in the centre. Okay? Now, it's not just planets and satellites that go in circles. It's electrons. It is cars going around circular tracks. So this is the centripetal force, and that's its formula down here. But that centripetal force is an apparent force. An apparent force is not the true creator of the force. The true creator of the force is that this centripetal force is created by another agent. And there is a whole list of different things that could be creating centripetal. We can have gravitational force. So gravitation is a force that makes things go in circles. So in this case, the gravitational force would equal the centripetal force. We can have the electrostatic force. That's the force between an electron and the positively charged nucleus. And that would create the centripetal force. We can have friction forces. I could keep on writing things down. All we need is a force to be acting at right angles to the direction of motion. So here, an object moves in this tangential velocity here. So this is the direction at any time that that mass is moving in. Okay? At the same time, it is pulled in towards the centre. And the angle between those two is 90 degrees. When this situation occurs, the object would automatically form a circle in its path. And it doesn't matter where it is on the path, it moves tangentially and pulled down, and we still get a 90-degree angle. So from the preliminary course, we know that this is the size of that centripetal force, and we know that the m is the mass of the object that is moving. This here, the velocity, is the tangential velocity, so it's that value there. And r is the distance from the centre, so there's the radius there. Okay? And you can apply this formula to a whole series, and in your blue book, you have to apply it to a planet going around the sun, an electron going around a nucleus, a conical pendulum, as well as a cyclist, I think it's a motorcyclist going around a curve, and just applying that formula over and over again. So as I said before, the centripetal force is itself created by another agent. Something else creates the centripetal force. And in this case, what we are looking at for this topic is the centripetal force is created by what other force? What's the big force that keeps the Earth going around the sun? Gravity. Gravity. Okay? The force that keeps the moon going around the Earth? Gravity. Satellites going around the Earth? Gravity. So the centripetal force in space is caused by simply answering this question, gravity. So here is the Earth, and it's pulled towards the sun. We know, according to Newton's law of universal gravitation, that if the Earth is pulled towards the sun, what's the sun being done to? It's being pulled towards the Earth. Equal and opposite, isn't it? But we are going to ignore that second force for this time because we want to just analyse the motion of the Earth, not the motion of the sun. The sun does move ever so slightly, but because it's so large, it apparently doesn't move at all. Okay? And remember when I say the word apparently, I'm not using it in our colloquial, conversational meaning. What does the word apparent mean? Right, it appears not to. Okay? So it appears. So I'm really meaning that the sun appears not to move from our point of view. In reality, it does wobble slightly towards us, just because we are pulling on it. Okay. So, just to take a few moments to use this and remind ourselves how to do all this force. Calculate the centripetal force on a mass of 1.5 kilograms, moving at a radius of 50 at a velocity of 20. We just simply use the formula F. In this case, the mass is 1.5 kilograms. Velocity is 20 meters per second. Please make sure you square that. That's my biggest mistake that I constantly make with this formula. I forget to square that. All over 50 meters. If we use the units of kilograms, meters per second, and meters, then the unit of force will become newtons. Okay? So often you are going to be told, especially because this is referring to planets, you'll be having the radius in kilometres or even in different units, so you must always convert it. You might have the velocity in kilometres per hour and so on. Please make sure you convert it. And what value does this one come out to be? 12 newtons. Okay? And you can fiddle around with it, and we can have a variety of different things. Here's one you're calculating different things with kilometres. I'm going to move across that. So we move on to now orbital velocity, because orbital velocity, once we understand circular motion and centripetal force, then orbital velocity becomes quite straightforward. So defining it, the definition of orbital velocity, the velocity at which a body revolves, turns, rotates around another body. Okay. And secondly, it is also the minimum velocity required for it to maintain an orbit. So we've already analysed Newton's idea of orbital velocity because we understand how he got to escape velocity. We know that, we know that if we were to do his analysis again, if we were to project off the top of our very tall cliff or very tall mountain, the ball that we project horizontally will hit the Earth. But given enough energy, it will go all the way around and re-enter the back of the cannon. So this is the value for circular orbit. Okay, that's at one. It's the minimum value to which you get. Anything less than this value, what will happen to the ball? Right, it will hit, if we would leave the mountain in the way, it will hit the back of the mountain at some point, okay, or it will hit the surface of the Earth. If it hits the back of the mountain, it might crash over here. If it doesn't hit the mountain at all, it crashes somewhere else. But that's the minimum value for which orbit is maintained. Larger than the orbital velocity, you will go off, but you'll come back. So you get different shapes of orbit until you eventually get to one point where you've given it enough energy and it goes off and never comes back. And what do we call that velocity? That's escape velocity. So when we are talking about orbital velocity, it's the minimum value of velocity for which it is required. You can keep on going, you get different shaped orbits, but the minimum velocity gives you what shaped orbit? Circular. Good. Okay. You have to be able to derive the formula for circular orbit. So to do this, we need to equate, and this is found on page 33 to question 5, where we have to be able to equate two different values, and get the formula for for orbital velocity. And the reason why I'm getting tongue-tied is because we're going to then have a look at it and say how close is this formula to the escape velocity formula. Right. A few moments ago we said that the centripetal force formula, this one over here, by itself, that's an apparent force. That's a descriptive force. It's a force that describes how a motion, an object in motion in a circle, must be acted upon. So that there just tells you what is the velocity required to maintain this force over here at this radius and this mass. But over here, what is the actual cause of the centripetal force? It is gravity. So what do I know these two values must be? The force of gravity here must actually equal the centripetal force. They're the things which are creating it. So the gravity force is creating the centripetal force, because they're one and the same thing. Okay. So what have I simply done in this line here? I have equated them. Good. Now, when you equate two formulas, you've got to make sure that the letters, the pronumerals we use in one part of the formula match with the pronumerals of the other. So let's just make sure that we are talking about the same thing when we talk about the R's and the M's and so on. What is R? Right, it's that distance there. Is that true in both of these formulas? Does that R and this R over here, do they represent the same thing in both formulas? Right. If they represent the same thing in both formulas, what can we do to them on both sides? We can cancel. We can cancel one of these, and there's two over here, so we just leave an R over there. The next we're going to look at is the M. And we're using the formula which has the little m and the big M, because I like that formula. It makes things more user-friendly, rather than having little ones with little subscripts, M1, M2. So let's have a look at this little m. What is the little m in the centripetal force? Mass of what? Right, it's the mass of the object in motion, which is that one out there. Let's go and have a look at the two m's over on this formula over here. What's the little m and the big M representing? Right, good. The big M represents the mass in the centre, and the little m is the mass out here. And this determines the force between them. Okay. They don't have to be rolling around in a circle. This one over here just represents the force between two objects. This one over here says, well, if they're going in a circle, they have to be the same. So now we know that the mass, this little m here, is the same as this little m over here. What can we do? We can cancel. And that leaves us with v squared equals g capital M on R. Square rooting both sides, we get v equals the square root of gm on R, which is the orbital velocity formula. Because this is a derived formula, it does not appear on the formula sheet for the HSC, so you either memorise it or know how to equate it and how to get it. Okay? It's very similar to another formula, and that's the reason why most of us just memorise it. Okay? Are we okay with that? Any questions? Right. So let's just have a look at what are the different conditions that create different orbital speeds. Remember, this is a velocity, it's a speed. And just depending on a few things, this will change. The first thing that it's proportional to is it's proportional to the mass of the central object, the mass of the object that you're orbiting about. So it's proportional to the square root of m. The second thing that it's proportional to is the radius of the planet, or the radius from the centre of the planet. So I shouldn't say the radius of the planet, it's the radius from the centre of the planet. And that's on the bottom, so it's 1 over the square root of r. Now, even though these proportionalities have square roots in it, they generally act the same way as direct proportionalities and indirect proportionalities. So, if I have a more massive planet, in other words, the planet's mass goes up, what has to happen to my orbital velocity? Right, it goes up. So, if I'm orbiting Jupiter, I have to orbit at a much faster speed than I would if I'm orbiting the Earth, for instance. What about the radius? As it goes up, what will happen to my orbital velocity? It will go down, because they're inverse, because one's the denominator, one's not. Okay? Which means that the closer you are to the central object, the faster you orbit. So let's just take a few moments and have a look and see, does that make sense with what we already know about our solar system? So here is the Sun in the centre. What's the next planet out?
Mercury.
Mercury. Okay, so there's Mercury. And then the next one out is Venus. Let's give her in orange. And then we'll put the Earth out here. And right out we'll put, good old Uranus and Neptune. We'll fix those up in a few moments. Okay, the Earth goes around in 365 days. Okay? How many days does Mercury need to go around? Do we know? Does anyone know off the top of their heads? Oh, very good. It was 88. For the people at home, they all knew it was 88 days. Okay. I can't remember what a year is in Venus, but it's somewhere between 88 and 365. Right. That means that Mercury goes around much faster than the Earth does. Does that make any sense? Why? Because it is closer to the Sun. Good, excellent. Jupiter goes around once every 11 or so years. And good old Pluto, if it was still in the planet, goes around once every 120 something years. Okay, yes, we all love Pluto, even though it's just a big chunk of ice. Okay. So, it gels. That means that if the radius of orbit is small, the velocity is quick. The radius of orbit is large, like Pluto, the velocity it goes around is slow. Okay? So, when we are orbiting the Earth, so here's our Earth. Put something we recognise on it. So yeah, it's a little bit greener than Australia normally is. I'll put a lot of desert in it. Okay, here's desert. Okay. Okay. You going to live on the fringe? Okay. You will, yeah. Rightio. Now, if I was to put a satellite here, and we'll call this a low Earth orbit, a LEO, L-E-O, low Earth orbit, that's around about 200 to 400 kilometres above the surface of the Earth. That's up to about 1,000. And then we put out a really big satellite out here, okay, far away, okay, and then the biggest satellite that goes around the Earth is the Moon, and that goes around once every 28 days, or 29 days approximately, and we call that a move, okay, which is a month. People at home, they just got why we call a month a month. Right here. A satellite in a low Earth orbit orbits the Earth approximately, if on average, about 1.5 hours. Between 1 hour and 1.5 hours, up to about 3 hours. So, these satellites whiz around the Earth. They are travelling at tremendous speeds. So they can take a full orbit around about 1.5 hours on average. Okay? These ones out here, these are the next very famous orbit is called the geostationary orbit, and those things take about 24 hours exactly, but we'll get on to why that's a very important orbit later. But that's at around about 42,000 kilometres away. Okay? Whereas this one here is only about 400 kilometres, so the radius is around about 7,000 kilometres all up from the centre of the Earth. So the further we are away from the centre of the Earth, the longer the orbit will take. Okay? Until we get to 250,000 miles away, which is the Moon. The Moon is about 250,000 kilometres, and it's more, it's like what my old car used to do. And that takes 28 or 29 days to go around the Earth. Okay? So we slow down as we get away from the central object. Okay. And finally, let's look at the two formulas that are derived from Newton's understanding of motion. Both of these formulas came from us understanding how to use energy and how to use gravitational forces and apply that to Newton's universal law. This one here, we equated Fc equaling Fg. In other words, the centripetal force equaled the centripetal force. This one over here, we equated EP with EK. Now remember, we got EP and EK, oops, we got EP and EK, I'm doing that, from Newton's understanding of his formulas, the universal law. So both of these formulas here and here are deriving from Newton's formula, which is simply force is capital G, little m, big M on R squared. So both of these formulas come from that somehow. Their origin is in that. This one is the velocity for orbit. This is the velocity for escape. What's the only difference between them? The actual answer is not exactly 2. It's root 2. So all you need to do is, now root 2 is approximately equal to 1.41, or just 1.4. If you have a circular, perfectly circular orbit, and just say, for instance, 1,000 metres per second for that orbit. If you were to multiply your velocity by 1.4 at that moment, so in other words, you increase your velocity to 14,000 metres per second from that orbit, what will you do? Escape. You will suddenly go off at a tangent and escape and never come back. So all you have to do between a circular orbit and an escape orbit, or escape velocity shape, which is the hyperbola, there is only 1.4 times a factor. And more, as you increase from 1,000, just remember I'm using 1,000 as a base unit. If I increase to 1,100, I would become more and more elliptical. As I get towards 1,300, 1,300, I become quite elliptical. And when I increase to 1,410 or something like that, I will zip off and never come back. Okay? So if you calculate your orbital velocity at any place, and you then multiply it by root 2, you realise that that's the escape velocity that you need to go away from that orbit. And that's how we do it in reality. If we need to put a satellite into Mars, we first put a satellite into orbit and then do a final rocket burn that will increase the velocity of the rocket by at least root 2. Once we've done that at the right time, and we've got some really good people who've done extension maths, they can do the right trajectory and they can cross it. Because if you do it in the wrong place, you go off into space and never come back. We want to go off to Mars, don't we? Or to Jupiter or whatever. Are we okay with the whole idea? So the formula that we have just derived is for what shape, once again? Circular. Okay? And the course just requires us to be able to do circular. Okay? So, there it is. I'll just pause there. Pause.